Yeah, ma'am.
Your screen is visible.
Okay,
Visible.
awesome. If I
Yes,
put it in slideshow mode, can you see my
Yeah,
bigger
yeah, it's good.
screen?
Yeah, it's
Okay,
good,
great.
ma'am. Yeah, it's good. Yeah.
Okay, awesome.
Okay, ma'am. Before starting the session, I'll give some guidelines to the participants. So after that, our session will agenda will be like welcome address will be given by our HOD sir. Then this webinar will be ending with an question and answer session. So I'll be giving some instructions clearly for the participants.
Okay,
So
sure.
good morning to all. So we welcome you for the session. The thing is like kindly mute your video as well as audio other than the organizers. So don't interrupt the session by means of any miscommunications. So let us start the session. Now our HOD sir will give the welcome address.
Hello,
Good
sir.
morning. Yes, good morning to all
Morning.
of you. I welcome on behalf of Chandigarh University and the Department of Aerospace Engineering, Madam Priyanka Srivastava. Ma'am, you are welcome for the session. And we are very much grateful to you that you have accepted our invitation and really accepted the invitation. And it is very helpful for us in this situation. You are going to talk about the cases and on. So I hope students will be inculcating lot of information from your lecture, as well as faculty also, because as Mr. Ajin was telling that it is our dream organization for all aerospace. We thanks again, once again, thanks for it. Now I will hand over to you. Thank you, ma'am.
Thank you so much for that introduction. Thank you so much. So, like Professor said, I am Priyanka. Hello, everyone. I am a space systems engineer at NASA's Jet Propulsion Laboratory here in Pasadena, California. And I have been working here for last 4 years. I went to Chandigarh, Punjab University for my undergrad. I got a degree in electronics and communications engineering, and then I came directly to the US to do my master's in space systems engineering from University of Michigan, Ann Arbor. Um, and right after my master's degree, I got an internship at JPL. So JPL is the Jet Propulsion Laboratory. And since then, I have been working over here and I've been part of a lot of almost 3 missions now. And so my today's talk will be focused on what space systems are all about and how have they helped us in exploring Earth, Mars, and the universe beyond. So I would first like to begin with uh, these pictures. Um, the pictures are of Earth and they were clicked. The left picture was clicked by the Voyager 1 spacecraft that was built by JPL in 1970s. And it clicked a picture of Earth, and it's depicted by this little pixel over here from about 6 billion kilometers away from Earth. And on the right hand side is a relatively newer picture that was clicked by Cassini spacecraft in 2013. Cassini was also built by JPL, and it was also able to click a picture of Earth uh, from Saturn. You can see the Saturn rings over here. So you can imagine how space systems have really enabled us to understand the perspective of our Earth in this gigantic universe. We're just simply a pale blue dot in this big universe, and the space systems, the spacecrafts, have helped us explore the universe away from Earth. The Voyager 1 spacecraft is still alive and it has reached interstellar space. It has moved beyond our solar system, and it's still surviving and is still alive, still healthy. And it's the first ever spacecraft to move beyond the solar system. And Cassini spacecraft, on the other hand, it finished its life cycle. Its mission objective was to orbit around Saturn, and we had to, as part of the mission, we had to retire it, and we crashed Cassini spacecraft in 2017. It was a very bittersweet moment for all of us at JPL, but Cassini helped us get really good scientific data of Saturn, which scientists will be cherishing for years and years. So now, what really goes into space exploration? There are three main pillars that help us in exploring space. The first is science. I guess always the main objective behind space exploration is that we want to find some sort of scientific investigation. We want to understand this atmosphere, not just of Earth, but of the different planetary bodies across the universe. We want to understand the biology that may or may not exist in places beyond Earth. Similarly, astrophysics, the geology. Then we have the engineering. Engineering is really where you start realizing spacecrafts or hardware or systems that can go and perform some sort of scientific experiments or some sort of scientific investigations for us. And on the third pillar is the technology. It's the future technologies, the robotics, the new kind of tools that our technologists provide that help us in advancing our current engineering techniques, and also help us in understanding how can we architect much better missions in the future. And so all three of these systems, all three of these pillars help us in making space systems. And these space systems have helped us explore Earth, Mars, and regions beyond Mars. Really, the region beyond the solar system, to be precise. So now let's move on to see what really goes into developing a space system. We try to step this development into these 4 simple steps. We first try to understand the mission concept and architecture. So this is where you want to think about what are the kind of objectives, the science goals or the engineering goals that you want to achieve out of your mission. And how would you really architect it? How would you really construct it? The second step is, how would you actually start building it once you have the goals in mind? How would you start building it? You need to have a design in mind. Once you have the design, you start developing that design. You start bringing all the components together to actually build that thing. Then you move on to the third step, which is integration testing, where you actually bring all those parts together and make the spacecraft that you want to use to achieve your mission concept and architecture. And then once your system is integrated and tested, we move on to launch on a launch vehicle or a rocket that takes you to your destination. And then you begin with your actual mission operations. So in the next slides, I'm going to talk through each one of these 4 steps and give you some examples from the missions that I have worked on. And I'll show you how I have been involved in the latter 3 parts of the mission through specific examples. So the first one is mission concept and architecture. So NASA JPL tries to first think about the operations, the concept of the mission. And this is uniform across every space organization, whether it be NASA, ISRO, any space organization first begins with some sort of concept in mind, some sort of architecture. And I have an example over here. The example you see is of a futuristic Mars sample return mission that we're actually working on. It's in the conceptual phase right now. And the idea for this Mars sample return mission is to start from the Earth, cruise in the space. So when I say cruise, it means that it's traveling. It's traveling in space. It has launched from Earth and it's still traveling in space. It hasn't reached Mars yet, still cruising. It will then land through some highly complicated engineering system. It will land. It will have this, you can call this a rover, a mobility system that will that can move around Mars, and it will go to our next rover mission, which is called Mars 2020 mission. So it will go and reach the rover that we're going to send this year, called Perseverance rover. So this rover will go to our Perseverance rover and collect some Mars soil samples from it. So you can see the handoff going on over here. This was the thing that will land in future. This is the rover that will land this year, hopefully, fingers crossed. And then there will be some sort of handoffs of Mars samples between them. That once those Mars samples are retrieved, the rover, the sample collector, will go on a ascent vehicle. So ascent vehicle will capture those samples of Mars soil, and then they'll send those Mars samples to a spacecraft that will be orbiting around Mars. And then that spacecraft that is orbiting around Mars that has collected those samples will return those, will carry those samples on the spacecraft. It will take it to an orbit around the moon, and then it will finally bring those samples back on Earth. So that's how we're thinking of having a Mars sample return mission. You can get an idea of how the conceptualization work happens. So that was conceptualization. Then is, how do you really start thinking about what are the kind of things do I need to build my system, to build this mission? We're not going into systems yet. This gigantic mission. How are we going to achieve this? So for any space mission, you first of all you need a subject. So when I say subject, it could be anything. It could be a mission to Earth atmosphere. It could be a mission to Moon. It could be Mars, Jupiter, anything. So you need a subject. Then you need a path to go reach that subject. So you need an understanding of the orbit and constellation that can take us there. Then you need a space element. So when I say space element, this is where I'm talking about the space system, the spacecraft that will have some kind of payload. And payload is something that helps in achieving mission goals. It will perform some sort of experiment, some sort of investigation in helping us achieve our mission goals that we thought in the mission concept. Then we'll have the launch element, which is of course really necessary because we need to escape the Earth's atmosphere. We also need a ground element to establish a communication link between our spacecraft and the ground station there on Earth, where we'll be receiving all the data, all the scientific investigations that our system has made. And then we'll need mission operations, where there are people sitting in the operations center receiving that information and controlling our spacecraft. Usually, spacecraft are autonomous systems, but we still need people to keep monitoring them, to keep seeing what kind of data is the spacecraft collecting, if it's healthy or not, if there are any sort of faults or anomalies that have arised in the system that we need to start working on. And then we also have the command, control, and communication architecture. This is where if you have a constellation of satellites working up in some orbit where they're communicating with each other, this is where we need to have a very a relatively complex architecture of the communications as well, and that doesn't include that just include the spacecraft. It also includes the ground network as well. So this is how you start thinking about the architecture and the different elements that go behind actually building your mission. So moving on, this was the first step. The second step is designing the mission, the system, and developing it. So once you have your mission objectives in mind, they could be scientific objectives, technical objectives, there could be some sort of programmatic constraints. Then need to start translating those objectives into specific requirements. Because if you and you need to define constraints in those requirements. So when I say constraints, it's supposed to be specific details of how you want to achieve, how you want to build your system. So let's say if you want the let's say I'll give you an example, a simple example of a car. You want a car to drive fast. That is not a requirement. You need to specify that I want a car that can drive as fast as 100 kilometer per hour. So this is where you define the constraint, that is 100 kilometer per hour. And you also ask the car to perform fast within that specific constraint. So we need to translate objectives into requirements. And so you need the highest level mission requirements that talk about your mission performance, your reliability, how much coverage in terms of science, in terms of mission objectives, how much coverage do you want? What will be the cost? What will be the lifetime? And then once you have the highest, oops, sorry, I'm getting this annotation request. So once you have the mission requirements, you then start working on to more finer details of the mission. So if you remember from the architecture diagram, we had these several elements that were more finer details of our mission. So in this third step, we start designing requirements for each of those specific elements. So what kind of orbit do we want? What is the power budget? If we have to stay within 500 watts during the cruise or during the surface operations, we need to keep those budgets in mind. How much should be the mass, the weight? It's very important to make sure that the launch vehicle can accommodate the mass of your spacecraft. What should be the configuration? So when I say configuration, it means should the spacecraft be in a horizontal kind of configuration, or should it horizontal configuration, or should it be in a vertical configuration? How would the solar panels be on top of the spacecraft? What will be the operation? Then at the same time, we need launch vehicle requirements. So we need to go and ask the launch vehicle people, what do you need from us? What do you need so that we can accommodate our spacecraft on your launch vehicle? So they'll tell us that we need so much, we have so much volume and you can only accommodate in that much space. We also have this environment. So when I say launch environment, I mean, you've seen, I'm sure a lot of you might have seen videos of how rockets launch. There's heavy vibration. There's a lot of thermal release, heat release. And so we need to make sure that the spacecraft that is inside the launch vehicle can withstand that harsh environment inside the launch vehicle. So we need those details from the launch vehicle. Similarly, we need to have operational requirements. So okay, you've built your spacecraft, but what are the requirements on the ground station that is receiving all that data? They also need some sort of requirements on their processing capacity, their processing speed, or the timing in which they should have people on computer so that they can monitor the spacecraft. Then this is the third level, and then we go one more step down further, where we start talking about requirements of the different subsystems that make the spacecraft. So this is where the thermal subsystem, your power subsystem, the structure that the spacecraft is made up of, the electronics, the GNC, which is the guidance and navigation control, the attitude control that stabilizes the spacecraft in space, the instruments. So we need requirements or design details for each of the subsystems because it's because defining just a requirement at higher level won't help us in understanding how we want to design the pieces and parts. So we need to understand how to design each one of them and then bring them all together to make the spacecraft. So I'm now going to give you an example of a mission that I am working on right now. It's called the Europa Clipper mission. This is NASA's next flagship mission after the Mars 2020 rover. And the mission is to Jupiter's moon called Europa. So Europa is supposed, so scientists around the world, they believe, and they've seen data from some past spacecraft missions that Europa might have a global salty water ocean, twice of the amount of what's on Earth. You can imagine if there is some sort of salty water in some other planetary body outside of Earth, it could be that there might be some possibility of life, some ingredients of life. And so we want, through the Europa Clipper mission, to really understand the three ingredients of life that could be present on Europa. It could be liquid water, could be the chemistry. It's not just the liquid water, it's also the composition of the compounds in the atmosphere that can help us understand if we can sustain, if life can sustain on a different planetary body, and energy. So the Europa is a really special planetary body, as you can see. We have these kind of special ridges and these special areas around the entire moon, which kind of hint us that there could be some sort of activity going on underneath the shell of Europa. So we want to send a spacecraft that can answer questions about Europa's ocean, ice shell, composition, geology, like what's going on, like why are these ridges around? Are these formed because of some movement of surface plates on Europa due to some sort of energy around them? And when I say energy, it's about how strong the gravitational force around Europa is. And as you all might already know, Jupiter has a very high magnetic environment around it. It's really hard to design spacecrafts that can survive in orbits around Jupiter because Jupiter's magnetic radiation is very it's very lethal. It can interfere in your electronics. It can destroy your power system. So we need to really make radiation hardened equipments that can survive in that environment. So this is our mission concept. This is our mission goal, objective, to go and investigate Europa. And in order to do that, we are building a Europa Clipper spacecraft. And this is a picture of how it will look like once it's built in the next 3 years. And it's equipped with almost 9 instruments, and some of them like one of the most powerful instrument is a radar, a VHF radar antenna, and that radar has the capacity to understand the ice, the ocean, which might exist underneath the icy shell of Europa. It's a very strong radar. It's called ice penetrating radar, and it can detect what kind of chemical composition lies underneath the icy shell of Europa. Along with the instruments, we of course have our thrusters that help in moving the spacecraft. We have the solar panels that will help in uh, generating power. And we also have the high gain antenna that will help in establishing communications with Earth. So, and on the right hand side, what you see is, is a picture of how the spacecraft will be revolving around Jupiter. So, you might be imagining that this is a mission to Europa. Why is the spacecraft orbiting around Jupiter? It's because orbiting around just Europa might cause radiation harms to the spacecraft. So we want to remain in a highly elliptical orbit around Jupiter. We want to stay as far from Jupiter as we can, but while orbiting around Jupiter, we'll make sure we fly by across Europa. So you might not be able to read properly, but this is Jupiter and this is Europa. So we'll be orbiting around Jupiter, but we'll be making flybys through Europa. And we'll be making almost 45 flybys. And in every flyby, we'll try to cover as much as of the Europa as we can. And the simulation shows you, like, these are the green lines that you see over here are the flybys where we'll be collecting science data, where the radar will be collecting some information about the ice shell, about the surface geology, about the different kind of ridges that are present on Europa while being on a Jupiter orbit. So this is how we're designing the mission architecture, the mission concept, and we're trying to understand what are the subsystems, the instruments, the orbit design, trajectory design, and we have requirements for each one of these elements. So moving on, once you have the requirements and everything ready, you now want to start integrating the hardware elements, the hardware and the software elements together to actually form your spacecraft. So you begin with your components and your units. So it could be your simple resistor boards, your brass boards that you connect with your tiniest electronic system, and then you integrate that electronic system with an instrument to collect data. So all these little units combine together to form our subsystems and our instruments. And then these subsystems and instruments integrate together to give us spacecraft. And one thing that I want to mention is that in this process of integration, we have to perform testing and analysis at every step. It's important because we need to verify the requirements that we chose in the earlier step, because you might be having a design in mind, but how would you really know if your spacecraft actually met the design? It's through verifying the requirements. So every level has a set of requirements, and so we'll be performing tests to check if those requirements have been met. And those tests will be scaled in size when we actually integrate the entire spacecraft together. So we'll be performing more end-to-end testing. And some of these example tests are functional tests. So is your spacecraft performing the same way that you thought of it to perform? Did you put your spacecraft through a thermal environment? And that thermal environment should be the same as the flight system as the flight environment that it will be moving through. And the thermal vacuum tests are really one of the main tests that every spacecraft goes through. And it's to make sure that your spacecraft can survive in flight temperatures, and pressure conditions. Then you have the electrical tests, just to make sure that all the knobs and switches have been connected correctly and are in a safe configuration. You have the flight software tests. You have the shock and vibration tests, because if you remember, your launch vehicle goes through huge amounts of shock and vibration levels. Electromagnetic compatibility tests. Because there is a lot of um, kind of exchange of electromagnetic signals between the spacecraft and the electronics units within the spacecraft and also the ground station, we need to make sure that none of those signals interfere with each other. So we perform electromagnetic compatibility tests for them. Then we have mobility tests. So mobility tests are for space systems that move. So rovers, they need to be tested for their mobility. If they're able to go from point A to point B with the required velocity or acceleration in mind, and is it able to conquer the obstacles that it's going through? So these are some of the important tests that we go through when integrating a spacecraft. And once the spacecraft is integrated, we then take that spacecraft to the launch vehicle facility, and then we try to hook up the spacecraft with the launch vehicle. And that's a very important step as well, because you want to make sure that um, that the spacecraft is safely accommodated inside the launch vehicle, and that it won't that the launch vehicle can provide enough integrity during the liftoff phase. And also, I want to tell you one thing, that while performing all of these tests, we want to make sure that we keep the spacecraft in a clean environment. We don't want any sort of dust particles, any sort of any external particles entering the spacecraft, because if your mission is supposed to collect samples, or is it's supposed to do any sort of investigation, then we don't want any kind of inappropriate mixing to occur. And we want pure data to be achieved, because that's what our goal is. So this was an example of how system integration testing happened. And I want to give you an example of another space mission that I was involved in last year, the Orbiting Carbon Observatory 3 mission, which is a instrument on the International Space Station. I'm sure all of you might be aware of it already. This is an Earth science mission, and this was my first mission where I was involved from the end-to-end testing, and it was launched last year. So it was my first mission to be launched, and it's up in space right now. And the goal of this mission was to collect carbon dioxide information from Earth's atmosphere, because the carbon dioxide relates to the growing urban population and the changing patterns of fossil fuel. And how OCO3 was doing it was with the help of 3 spectrometers that were measuring the intensity of sunlight reflected from the presence of CO2 in a column of air. So you can imagine this to be the International Space Station ISS, and it was measuring the amount of sunlight that is reflected back due to the presence of CO2 back to its spectrometers over here. So I was involved in integrating the entire OCO3 instrument together, and it's relatively smaller in size as compared to our bigger Earth science or bigger Mars or Jupiter missions. It was a space instrument, and it's currently on ISS. The last picture that you see over here is from a thermal vacuum chamber test. So the instrument was covered in a thermal blanket, and it was then kept in a thermal vacuum chamber that you see over here. This chamber was able to replicate or simulate flight temperature extremes and flight pressure conditions, and then we were able to see how is our instrument functioning in that environment? Is it still able to collect data using the spectrometer? Is it healthy? We also tried to inject some faults just to see can our spacecraft survive in a anomalous situation in off nominal scenario. So we had to deliberately put in some faults during these high level testing scenarios just to see how robust, how capable our system is. And then similarly, I worked on another mission, which is launching this year, is the Mars 2020 rover mission. And it's a highly complex mission, and I have tried to depict it into three basic parts. One is the heat shield that contains the descent stage and the rover. The second is the descent stage, which consists of the entry, descent, and landing system. So this descent stage actually binds the rover with it, so that once the heat shield reaches Mars atmosphere, it can release the rover through some sort of mechanism down on Mars surface. Then we have our Perseverance rover, which is a follow-up to the Curiosity rover. You might have heard of. It was launched in 2012, and Perseverance rover is going to launch this year, and it's also equipped with several instruments. And this Perseverance rover is going to collect Mars soil samples, and it's going to collect those samples so that in future, when we have a Mars sample return mission, that mission can collect these samples from the Perseverance rover and then bring them back on Earth. So because this is a highly complex mission, we had to perform piecewise testing on each of these three systems. And in the next slide, I'll show you how the test drive of the integrated Perseverance rover looked like once it was finally integrated together. We were trying to move it through uneven surfaces just to see how robust our wheels are. Trying to make it do a turn over here. This was the first full end-to-end test drive of the integrated Perseverance rover. On the right-hand side, you can see a picture of the descent stage and the rover tied to it through a tethered system. So this was a separation test that was performed to check can our descent stage safely lower down the rover on the Mars surface. And the tests were successful, and we've already sent the rover, the heat shield, and the descent stage to Florida, from where it will launch this summer. And then comes the last phase of developing a mission, the mission operations. So once you've sent your spacecraft for launch, it's liftoff, it's up in it has escaped Earth's atmosphere, then that's when the mission operations begin. So we have another dedicated team of engineers who are just solely involved in mission operations, and they monitor the day-to-day operations of the space system, its maintenance and support. And depending on your spacecraft, it might be performing either some sort of cruise operations, some sort of orbit insertions. So when I say orbit insertion, imagine if you have a mission to the moon, then once you escape Earth's atmosphere, you need to enter the orbit around Moon, and that event is called lunar orbit insertion. Similarly, when you have to perform any Mars mission, you need to perform a Mars orbit insertion. And for the Europa Clipper mission, where my spacecraft is going to go into Jupiter, we will be performing a Jupiter orbit insertion then in the Europa flybys. So yes, we have encounters or flybys. Then we have entry, descent, and landing. So if you're planning to send a rover to Moon, to Europa, to Mars, you need to have you'll be your system will be performing some sort of entry, descent, and landing operations. They'll be performing some sort of surface operations depending on what they want to achieve. If they want to collect soil samples, or if they just want to drive and click pictures and do some sort of monitoring of the atmosphere. And then comes the last phase of operations, which is the disposal. This is where the mission needs to decide that after the end of life cycle, after the end of mission life, do they really want to dispose of, or do they want to extend the mission life and perform additional activities? So all these operations um, help us in performing activities that can help us eventually meet our mission objectives and our mission goals. This is how the entire life cycle of our space system is. And I would like to show you a entry, descent, landing operation of the Curiosity rover that landed on Mars in 2012. I still remember I was glued to the TV when they were showing this um, landing event, and I was all fingers crossed and hoping for a successful entry. So this video will help you understand what are the different kind of operations that went into the entry of uh, of the Curiosity rover on Mars. This is when the Curiosity started its operations. So hope you guys enjoyed that video. And this was Curiosity rover's animation. And this is how the landing actually happened as well in 2012. And now we have our fingers crossed for Perseverance rover, which is almost exactly like Curiosity, but has better instruments. And it even has the capability to store sample tubes that will be having Mars soil in its belly pan underneath it. And so we're hoping to have a successful entry, descent, landing for Perseverance rover, as well as it is one of the most difficult operation. Even though we have landed multiple times on Mars, multiple time on Moon, entry, descent, and landing is always the hardest part. And you might have seen the example with ISRO's mission as well, that it's always hard to get a successful landing on any surface. So it's always a nervous event for engineers who worked years and years on the space system. And with that, I would like to thank all of you for dialing in, and Professor Vasu for setting this up, and the entire Chandigarh University for letting me talk to all of you. And what you see over here is a picture um, that was clicked by astronaut Christina Hammock on the International Space Station. So what she did was that when OCO3 reached ISS, she put a picture of all the mission team members, and there's me over here, the tiny little me, on her tablet, and then she put that tablet on the window of ISS. And then she clicked a picture of her tablet with the Earth in the background. And it's a very special picture for me because the Earth looks beautiful, and it's just a very special moment for all of us. And with that, thank you so much, everyone, and I'm open to questions.
Thank you, ma'am, for the lecture. It was very nice. So I request the participants, those who are having any queries, do drop your questions in the chat box so that I can read it out for you. So those who are having any queries, please text it on the chat box so that I can read it out.
Hello. That's a very good question. Yes, we have we as engineers, we have to face this major challenge of making our space systems go to environments that we have never been to. So what we do is we try to make our system being designed to the worst case possible scenarios. And also we try to use data from past projects, from past missions that might have flown through that environment, that might have not, they might have not really specifically gone to that planetary body, but might have flown past through it. So we try to, for example, we try to put as much as radiation hardened elements in our spacecraft. We try to um, make sure that our trying to think of a better example. We try to read through scientific papers that can help us understand what the atmosphere of a specific planetary body is, so that when we try to actually land on that planetary body, we have some sort of idea of how to prepare our space mission, our spacecraft for that. So a lot of scientific paper reading, data from past missions, um, designing our system for worst case scenarios, the way to go. That. So if you remember, so in one of my slides, I showed you a thermal vacuum chamber test, thermal vacuum chamber. So that is located at JPL itself. And so we have been able to place a lot of our big spacecraft inside that chamber and simulate the thermal environment, pressure environment. We also have kind of simulation systems for communication data grounds at JPL itself. So you all know that the communication data grounds are spread across the Earth, so we cannot really go to each one of those Earth locations to test our system compatibility with those ground networks. So JPL has a ground network simulation system. We also have vibration and shock generating platforms on which we can mount the spacecraft and make it go through several Gs shock environment and check if the spacecraft can survive in that harsh dynamic environment.
Okay, ma'am. The next question from one of our final year students. His question is, while doing flyby to Europa, how you are going to keep Europa's gravity to capture the orbit of spacecraft?
Europa's gravity to capture. So that's the thing. So the spacecraft is going to be in a Jupiter orbit. So it's going to be revolving around Jupiter gravity, and that is going to prevent the spacecraft from falling into Europa's gravity. That's the plan, to stay within Jupiter's gravitational orbit. And Jupiter has one of the strongest gravitational orbits. So we know that once we're in there, it's really hard to get pulled out of that gravitational orbit of Jupiter.
Okay, ma'am.
That answers your question.
Yes, ma'am. The next question is, like, what are the possible internships available in JPL?
Yeah, so I think Professor Vasu also asked me this question in the beginning. So usually for non-foreign national, for US citizens, they have a lot of opportunities available. They can work on space systems, hardware side, software side. We have IT work as well. We have robotics work as well. But for foreign nationals, I've seen a lot of students from India coming for doing more robotics engineering. So they've been working on more high tech technologies that will be incorporated in the future space missions. So they've been involved in a lot of machine learning and data AI sort of technologies that we've been using in our space systems.
Okay.
And so, if you want to apply for internships, you can always go to JPO's website, and I can send you all that link. And also reach out to the engineers that you feel most connected to. Try to contact them on LinkedIn. And try to see how you can share your resumes with them and show them hands-on experience, so that you have something to show them. It's not just asking for an internship. Just show some sort of skills before applying for internships.
Okay, ma'am. The next question is, how much time it takes to communicate to Voyager now? What will be the frequency used for data transfer?
That's a good question. I think I'm not sure. I think it does take around a month. I'm not sure about the exact date, and neither am I sure about the frequency. Sorry, I would have to check. Uh, but it's one of my favorite spacecrafts for sure.
What is the role of system engineer, which plays a major role in development of electronic subsystems?
So we have space systems engineer at every level. So if you remember from my diagrams, we have subsystem instruments, we have spacecraft level, we have mission level. So we have systems engineers at subsystem levels as well. So we have electrical engineers who are systems engineers. We have computer engineers, and their responsibility is to make sure that they can interface properly with other subsystems. If you're an electronics major, if you're an electronics engineer, can you make your system work with the power subsystem person? So that's the role of a systems engineer. Can you interface your subsystem with the other subsystem in the most efficient way?
Okay, ma'am. The next question is, as the actual data varies from the ideal one, say example, escape velocity, how do we determine the requirements? Like
Sorry,
from the
again.
actual case and ideal case.
Um, I'm trying to understand this question. Actual data varies from the ideal one. How do we determine the requirements? So I guess so if I'm understanding your question correctly, you're saying if we have sufficient escape velocity to make sure that our spacecraft can go outside Earth. I'm not sure, but I think so. What we do in terms of designing requirements is we make sure that we put in the worst case design constraints. We have a margin, we have a budget around which we design these requirements. And so, if we know the range, the most favorable and the most kind of the most unfavorable or the worst case scenario, then we can design a system across that specific budget. If that's the question.
Okay.
So even if it varies from the actual data, your system will be still robust to the changing escape velocities. It will still be able to escape because your system was designed around a good margin of requirement.
Okay. The next question is, for a Mars mission, Earth mass radio blackout is a major problem. Can we define an extended solar radius to solve the problem?
I'm sorry, can you repeat that question?
Yes, ma'am. For a Mars mission, Earth mass radius blackout is a major problem. So, can we define an extended solar radius to solve the problem?
I think I apologize. I am not well versed with designing uh, kind of the trajectories around the solar radius.
So, what are the plans to meditate space debris, remove space debris?
I think that's an interesting question. So we do have a lot of missions that are in conceptual phase right now, and as of right now, JPL doesn't have any mission that is being developed, but we will be having future missions for space debris removal.
Okay, ma'am. Okay, now I request Vasu sir to convey the vote of thanks for the session.
Yeah, hello. Hello, ma'am.
Hello.
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 Yeah, ma'am. Thank you. Thank you so much, ma'am, for accepting the invitation on behalf of Chandigarh University and students of Chandigarh University and management. So I thank you for accepting our request and sharing some valuable information about the work which is going on in NASA JPL. Yeah, ma'am. I really thank you for that. So sorry if I could have disturbed you messaging. So
No,
sorry
I
if I
think
have disturbed you.
no, it was my complete pleasure to interface with you all, and I apologize if I was not able to answer all of your questions. I think this is a very vast field, and we all are learning. And this is the main message that I wanted to convey today: is that it's all about learning every day, getting as much hands-on experience as you can, and don't be afraid to ask more questions and try as much research as you can. And thank you
Yeah,
so
ma'am,
much, Professor Vasu.
yeah, ma'am. Thank you, ma'am. We wanted our extended support in near future.
Yes, definitely.
Yeah.
Definitely.
Sure.
And you can always email me with more questions. Professor Vasu already has my email. So if people have any additional questions that I was not able to answer today due to shortage of time, I can answer them offline as well.
Sure, ma'am. Sure.
It has been 1.5 hours for the session. Thank you for your patience, ma'am. Once
Thank you
again.
so much, ma'am.
Yes. Thank you so much. It was really fun talking to you all. Thank you.
Thank you, ma'am. Thank you so much.
Thank you.
Okay. Bye.
Bye, ma'am. Bye.